definitely have a problem here, right? Since we have two number 5s. And let's see, this is number 2. So what number are we missing? 1, 2, 3. So 4 has not been identified anywhere. All right. So this is one of the most important sentences you want to take out of your class activities from the last class. This is on the first class activity. It's in bold. So this is something you should have in your notes that you should be using. This helps you to do what we just did, which is to identify or match a function with its equation, a polynomial function with its equation. So let's go through this. In general, if a polynomial, f is a polynomial function of degree n, then the graph has at most, that's a very important language, because at most means it's the maximum number, but it doesn't mean it has to have that. At most, n minus 1 relative extrema. What does relative extrema mean? Beside turning points, what's another name we've given for those? Yeah, relative maximums or relative minimums. So these are your relative maxes and your relative mins, which the other day we called turning points. And at most, n real zeros. That's another important word, because after today's discussion, the rest of the week, we're going to be talking about complex imaginary zeros. So this will change. So this just means at most, it can touch, it will have at most this many real zeros. That's the 0 is the value of x that makes your function 0. That's why it's called 0. Real means it's a real number, okay? And after we review the complex number system, that will change. All right. So the first thing when you look at these equations, you want to think about n behavior. When the degree is even, your arms are going in the same way. Your n behavior is the same as you move towards positive and negative infinity, okay? So if it's odd, we know that we're always going in opposite directions. Remember, I was walking around with my arms going in different directions. The other thing here is number 1 is the only quadratic function you have in all 6 of these. So that should have been one of the ones that was most easily identified, because it's the only parabola. So that has to be this one right here, okay? So let's take a look at this sentence we just looked at. So here's a quadratic equation. It says it has at so that what's the degree of this quadratic equation? What's the degree? N equals what? 2. So this says it has at most 2 minus 1, 1 turning point, which is exactly correct here. We have 1 turning point. It's located at 1, 0. That's what we call our vertex. It's also our turning point. And in this case, you could actually call that the minimum of the function. It's the absolute minimum. You don't get any point lower than this. We don't even have to use the word relative minimum. It's the minimum. And it's also the minimum. So the minimum value of this function is 0. The minimum is 0. We're only interested in the output value. The minimum value here is 0. It happens to occur at x equals 1. Okay, let's take a look at the rest of this. And it has at most, so the most number of real zeros it would have is 2. But in this particular case, how many real zeros does it have? 1. And what is the real 0? 1. X equals 1 is the real 0. That's where your function is equal to 0. It's also what we typically identify as the x-intercept. And what's the multiplicity? What's the multiplicity of that 0? Just from looking at the graph. If you zeroed right in there and just blew up that, what kind of function would it look like? A parabola. So what's the multiplicity? 2. Okay, I'm going to go off record here. So this has a multiplicity of 2, and if you factor this, remember that's the only way we get to see the multiplicities is when it's in factored form. If you just rearrange this so it's in descending order, that looks like this when you factor it, x minus 1 to the second power. Once you factor it, you can find your 0. This is 0 when x is 1. That's what the graph showed us. 1, 0 was the x-intercept. And there's your multiplicity, 2. So that's why it turns around at 1, 0. It never goes through, turns around. Now, I can't go through that kind of detail with all of these. But what we just did, I'm going to do it one more time. That's what you should be able to do with all 6 of these functions, is you should be able to look at the graph, you should look at the equation, see what the end behavior is, see what the zeros are, identify the zeros and their multiplicities from looking at the graph. So that's number 1. That's equation 1. Let's look at 2. This equation is cubic. If you put it in descending order, it would be negative x cubed plus 3x. Your leading coefficient is negative. That means your right arm is down and your left arm is up. So you're looking for a cubic function that has, as you move towards negative infinity, you're rising to the left and falling to the right. So as you look through these graphs, there's only one function that rises to the left and falls to the right, and that's c. So that's equation 2. What else can we tell about this? This is something you should do for every single one of these graphs. And that's all I'm going to say. I'm going to do it for 3 of them. What are the zeros of that function? What are the zeros, even if you have to estimate? Negative 1.8, and the other one is 0 and 1.8, approximately. Okay. What are the multiplicities? How do you know what the multiplicity would be? If this was in factored form, it would be the exponent on the factor. How do you tell it visually? If you cross the x-axis, you're changing the sign of your function. In this case, your function prior to negative 1.8 is above the x-axis, so all your outputs positive. And to the right of negative 1.8, you're negative. That changes sign. That means you have an odd multiplicity. And since you go straight through, it would have the exponent 1. Same thing is true with 0. And same thing is true with this approximately 1.8. So what that says is if you were to factor this, you should have 3 different factors. 3 different factors because you have 3 different zeros, and the exponent on all of the factors would be 1. What would be the value of A? If I put it in factored form, what would be the value of A, the leading coefficient? Other than Gabe. Almost. Negative 1. The value of A never changes between your standard polynomial, your polynomial form and your factored form. A always stays the same, which is negative 1. So let's take a look at this function for 1 minute. You have enough behind you to factor that function. The only way you can factor that, you set it equal to 0 because we're trying to find the zeros of our function. We're trying to solve this equation. You could pull out a negative x, and you would have x squared minus 3. You set each factor equal to 0. X equals 0 is one of your zeros. So if we were doing a little chart with our zeros, that would be one of them. Notice I don't put the factor in, I just put the value of x that makes the factor 0. And that has a 1 on it, so its multiplicity is 1. And that means I know at 0, 0, I cross the x-axis. That's what it tells me if I were to graph. Now this one, when you set it equal to 0, x squared minus 3 equals 0, you have two answers. You can either factor this so it looks like this, and see that you have plus square root of 3 and negative square root of 3, or you could use the other method, and hopefully you won't forget that when you square root both sides, you've got plus and minus for your answer. So these are the exact zeros, plus square root of 3 and minus square root of 3. Gabe gave us an approximation. Let's see how close Gabe was with the negative 1.8. So let's see what an approximate would be for square root of 3. Oops, that's good, Linda. Square root 3. 1.735, not bad. All right. So I wouldn't be asking, if I gave you a question like this on a test or an exam, I wouldn't be asking for an approximation. I'd be expecting you to factor it and give me the exact zeros. These all have multiplicity of 1 since the exponent there is 1. So if you were to factor this completely, this is what it would look like. F of x equals negative x cubed minus plus 3x. To put this in factored form, the negative 1 comes out because that's your leading coefficient, and you would have x times x plus square root of 3 times x minus square root of 3. Notice all of these have 1. When your polynomial is in factored form, to get the degree in factored form, you add up all of the exponents, 1 plus 1 plus 1, and that matches the general form right there. Right. So I'm going to stop there. I would urge you to go back and do the same thing, and also check out, let's check this out again. So this has degree 3. It says it has at most 3 minus 1 turning points. So it has at most 2 turning points. Notice here's a relative min, here's a relative max. That's 2. It's always 1 less than the degree. And what does it say? Has at most 2 real zeros, and there has at most 3 real zeros. 1, 2, 3. Okay. So that's the kind of thing we did number 1, and we did number 2. Later on today, as soon as you can, see if you can perform the same thing with these equations here. So today's class demo, today we're going to continue our work with modeling. And so far has been modeling with a straight line. In your very first project of the semester, we did modeling with a straight line. And as data changes, we know that not all data lines itself up in a perfect straight line. So we're now going to start looking at polynomial equations that might fit our data. So this table shows us the number of women in the full-time civilian labor force in millions, with children under the age of 6 for certain years. So I looked at every 5 years from 1975 to 2000. And this was the number of working women with children under the age of 6. Now, just looking at the data, you can see that it increases as we move from 1975 to 2000. So I used GeoGebra to create a scatter plot. Remember, the scatter plot is just these 6 points. And then I said, well, let's try to fit a straight line to that data. That's the red line right here. And as you can see, that models that data pretty well. That line is very close to each of these data points. So a linear model wouldn't be a bad idea. So I decided, well, this looks like it kind of comes up and it's starting to flatten out. Let me just try a quadratic. So I did a quadratic model, and that's this blue line. And as you can see, that's really close to the points as well. Now there is, in the past, we would have students put this in the calculator. And if you recall, with the straight line, we got a correlation coefficient R, right? It was between -1 and 1, and it told us how good a fit it was. Well, when you start looking at things other than straight lines, you look at something called R square. So if we were to compare the R square for both of these models, the R square for the quadratic would be a little bit better than for the linear. Okay, just a little bit better. And for some reason, we couldn't get the y equals in here, so we'll just put that in, because we always want to have an equation, y equals there. Okay. So the question today will be, how could we determine some answers or estimates or predictions from each of these models? And in the long run, so we're talking about end behavior. In the long run, which of these models would perhaps make the most sense to use, if any of them? So let's take a look at the rest of the questions here. So let's put down the equation for the regression line. So y equals 0.2111x plus 3.9919. It's important when your units are in millions or hundreds of millions of people or whatever we're looking at, that you carry that out 3 or 4, 5 places, because you're talking about millions of people. So if you estimate that and just call it 0.2 or 4.0, you're losing hundreds of thousands of people when you actually compute your answers. So you want to carry that out some number. And if this is in your calculator will have it out at least 7 or 8 places. All right. I always, to remind myself, put a y hat. I put that little hat on y, and that reminds me that it's an estimate or a prediction based on a model. It's not the exact real value from the data of y. So that always helps me, and that's what we do in statistics versus an algebra class. So let's write the equation for our regression parabola. That is y hat equals negative 0.0048x squared plus 0.3799x plus 2.8662. Okay. So as you can see, and this is going to be one of the things we talk about later, the linear model is the simplest model you could have for estimation. The quadratic isn't that much more complicated, but it requires a little more work if you're doing it with your calculator by hand versus having a calculator or a computer answer these questions. So let's use the linear and the parabolic models to predict the number of women who are working with children below the age of 6 in the year 2011. Well, what's the best we can do? We know what it is in 2000. So we would have to go, we're going to predict now. So our data only goes to here, 35 years out. Excuse me, 25 years out from 1975 to 2000. We're going to go another 11 years beyond that. So which of these models do we think would be the best estimate for that prediction? So let's take a look. So someone want to help me figure out how I would use the linear model to predict the number of women in the workforce in 2011? What would I do? Wouldn't I what? I'm sorry, I can't hear you. What are the numbers? I'm trying to find. Oh, okay. Yeah. Okay. And what value would that be? No, excuse me, what variable would that be? X. X is the number of years since 1970, right? Number of years, look at your x-axis, which is labeled right there, number of years since 1970. So 2011 minus 1970 is 41. Right? So that means when I use my linear model, y hat equals 0.2111 times 41 plus 3.9919. That would be my prediction using the linear model for 2011. So let's see what that comes out to be. Okay, so what do we have? We have 0.2111 times 41 plus 3.9919. So we have 12.647 million women. 12.647 million women in the workforce. That little symbol's for women. I'm getting lazy. Okay. Now let's use the parabolic model. The parabolic model says take the number of years since 1970, 41, square it, multiply it by that negative number, and then add this number to it, and then this number. Let's do that. So again, it's a little more to put into your calculator, but again, you're not doing the work, right? 0048 times 41 raised to the second power plus 0.3799 times 41 plus 2.8662. 10.3733 million women. That's very different, two very different estimates. Okay, two very different estimates. Now, we could go back, or we could ask the librarian to go into a database and actually find out how many women were in the workforce in 2011 to see which of these models would be the best. But let's suppose we're only back in like 2004. All right, 2004, we're back in 2004, and we're trying to figure out if 10.3 million women is a better estimate or 12. So based on the data, and if you were, you were interested in this, you would probably have a sense of what was happening in the workforce. Okay. Which model, if you had to make a choice, which model would you choose at this point to make the prediction for 2011? Which model would you choose? There's no right or wrong answer here. Okay, just so you know that. It's what you think. Someone other than Gabe's going to talk to me today, I think. And you would use linear Y, Kim. Why would you use this model? Okay, so we're 41 years out, so let's just look at this for a second. And again, there's no right or wrong answer. There's maybe what I would choose. So here's 41. I'm just going to put a straight line through. So here would be our two estimates based on the model. Okay. And what do you notice about the number of women in the workforce? What's starting to happen? There was a really big jump, in the first decade or so, but what's starting to happen to the data? It's starting to level out, right? So if I were to choose, that's me. If I were to choose, I would actually choose the parabola out to 2011. But if I went out to 80 years or 70 years or 60 years, look at the end behavior of this parabola. In the long run, the end behavior is going to eventually say that there's what? Negative women in the workforce. This is going to come down and become negative eventually, which makes no sense. It's meaningless. So this is where you would start to have what we call a word we learned in the very first or second lecture, breakdown, a class, I should say. This is model breakdown. In the long run, that's That's what we've been calling the end behavior. We know that's one of the things that we have to keep in mind about all polynomial functions. We know they're either going to rise in the long run or fall. So we have to know something about our data to see if that makes sense. All right, so let's take a look at this next question, which addresses that. Use the leading coefficient test. The leading coefficient is negative. The leading coefficient is negative 0.0048. So it's less than 0. And the degree is a parabola. So that tells us that the end behavior of this parabola is going to be going down. So if we had to use this deep into the future to predict the number of women in the civilian force, we don't even know if it's going to continue to rise. So much of that depends. But the trend is that it's going to rise. Which would I use? I probably wouldn't use either one. Frankly, I'd want to get more data to see what's happening. But I certainly wouldn't use the quadratic model to say predict 2020. If I were using anything for 2020, I would probably use linear, but I would be skeptical, right? I would be a little skeptical because the rate that this is rising, is what? What number is this? This is approximately 200, a little more than 200,000 women every year. That's what the slope says. 0.2 million, right? Am I right? Is it 200,000 is 0.2 million? Okay, so this is saying that this is the number of women increasing every year. I'd probably feel a little more comfortable with that than what would 2020 be? That would be 50 years after 1970. So I'd be looking at this prediction right here, which would then say I'd be down maybe in the 8 million again. That might be possible. Maybe more women and men are choosing to stay home and be parents, coming out of the civilian labor force. Okay, so this model wouldn't this model is a little out of date too, because now men are choosing to stay home and be parents. So this is just looking at women. So we really don't know. I don't know. For 2020, I might still stick with the quadratic. I might reassess that. 2020, I might just say I'd stick with the quadratic because it's still right around. Remember, that vertex area is flattened out for a number of years. That's one of the things I'm trying to point out to you, is that sometimes it's really clear looking at the data, the scatter plots, what you would decide. Other times you just have to explain why you would choose a particular thing. It's almost like, unless it's really clear and you're going in the opposite direction, so to speak, this is like really just you're putting together the information you know and explaining why you choose a particular model. So what we've done is we've eliminated the calculator from all of this, and we've given you the data sets and the scatter plots. But these are sort of, if you were to model some data, you want to create a scatter plot. And when you look at your scatter plot, you want to say, hey, what would look better there? Would a line fit that data better? How about a part of a quadratic? Or maybe part of, if it had a couple of turning points, maybe a cubic. Okay, so this is where you use the idea that we just looked at about the number of turning points. How many peaks and valleys does it have? Those are your relative maxes and mins, to determine what degree you would use. Then you would find an equation for your model, whatever model you choose. We're going to let the calculator and computer do that for us, whether it's GeoGebra or a calculator. So you're not going to have to figure that out. You're going to verify that your equation has a graph that comes close to the points. You're going to put the equation in. We're going to see what it looks like. And you want to make sure that it's close to the points. And if not, you might just want to reconsider the model that you chose. And then you use the equation to predict or make estimates. And because here's the most important thing that makes a big difference between some of the earlier regression that we looked at. because the end behavior of higher degree polynomials, so if you had fourth degree or fifth degree polynomials, they tend pretty quickly to increase or decrease, rise or fall. So extrapolation, what was extrapolation? That's what we were just doing, going outside our data set and trying to make predictions in the year 2020 or 2040, going outside your data set. So any kind of extrapolation-based predictions are usually inaccurate, and it's subject to a higher risk of producing meaningless results. Okay, so we just have to be careful, and this is true for any type of modeling we do. In fact, if you think about some of the recent headlines about global warming and the melting of the ice shelves in Antarctica, the models that the computer models that we've used so far have not predicted the incredibly rapid melting rate. In fact, there was just a big article in the Times about a week and a half ago, and it said computer models, and I'm like, oh, I wish we were doing modeling right now in 107, because this is like real stuff, folks. The computer models are now predicting that the rise in sea levels are going to be happening much sooner, much quicker than anyone had predicted. So anybody living along the Atlantic or any sea coast, right, town or city like Miami, Atlanta, Boston, right, all of these cities are in danger. But there's also, remember, islands that are particularly located in the Pacific that are either at sea level that are just going to be, and they're already starting to be totally covered. You know, so a lot of the Malaysia, all of these areas, and particularly where there's a large concentration of poor people, they're going to be the first people to suffer. You know, they'll start doing crap in Miami and Boston and New York with trying to raise, you know, sandbags and all that. But eventually, if this continues, nobody's going to be able to stop it. And it's going to be one of those things that once it starts, it's just going to continue at a pretty rapid rate. So this idea of modeling is not just something that, you know, you're having to do in a math class. You will, whatever area you go into, whether it's a business area where they use models all the time, or whether you're in a STEM field, science or technology or engineering, math, you will be working with models quite frequently. So how do you select a model? At the beginning of the modeling process, we must decide whether a linear, quadratic, cubic, quartic, or none is suitable for modeling the situation. Here's some criteria. These are just guidelines, folks. The graph of the model should fit the points well. Use the simplest model that captures the pattern of the data. Use the simplest. The model should make sense within the context of a real-world situation. So what that means is with this women in the labor force, if I was only talking 40 or 50 years out from 1970, either of these models would make sense. If I go beyond that, the model, like out 70 years past 1970, this quadratic model is useless. And probably so isn't the linear. So what I'd have to do is I'd have to get that data and try to fit a new model to it, to try to capture whatever's happening socially, economically, culturally, in whatever country we're looking at. So I think that's all you need for today's class activities. Let me know if you have any questions. Briefly discuss one of the major pieces of information you should have taken out of your last class activities. This was from number 1. I cut and pasted it directly from number 1. Is if you have a polynomial function of degree n, then these are the things that you can determine about that polynomial function. It will have, and the language is very important, at most, it will have at most n-1 relative extrema. The relative extrema, remember, is the relative maxes or the relative mins. So this means your relative maxes or your relative mins. We called those the turning points. Peaks or valleys, there's lots of little names you could give to that. So at most, you would have, for example, if we look at number 6 here, equation number 6, what's the degree? 5. So what's the most number of turning points this can have? 4. Okay. Doesn't mean it has 4. It means it can have at most 4. So if you look at these graphs, the only graph that has 4 turning points is right here, letter E. It has 1, 2, 3, 4 turning points. So that has to be minimum degree that this polynomial can be is 5. That's the minimum because it has 4 turning points. It could be a 7th degree, it could be a 9th degree, but the minimum, the smallest degree this could be is 5. So just from looking at that graph, and since this is the only 5th degree polynomial, this has to be E without any other, unless I was fooling you and I said, okay, there's going to be some equations here that don't have a match. But every equation here has a graph that matches it. The other thing you know about looking at E is that the leading coefficient, which is 1 here, because it's always the coefficient of your highest degree term, is positive, and when it's odd, that means your right arm is up and your left arm is down. So as you move towards positive infinity, your graph rises without bound, and as you move towards negative infinity, your graph decreases without bound. So that's what that first part of that phrase means, is of that sentence, is that tells you the maximum number of turning points. Again, it doesn't mean it has to have that many. For example, if you look at a cubic function like this, a cubic function, if a polynomial has degree 3, it can have at most, how many turning points? No. N minus 1, which is 3 minus 1, which is 2. At most, 2 turning points. Okay, but it doesn't have to have 2. It could have 2 on 0 turning points. So if you look at your parent function, f of x equals x cubed, your parent function is always increasing. It doesn't have any turning points at all. It's always increasing. It flattens out as it approaches the origin. So this has 0 relative maxes or mins, 0 extrema. Okay, but if I quickly graphed this particular cubic right here, this cubic, as you can see right here, has 1, 2 relative maximums extrema. All right. So when you go to match up these graphs, there's a lot of information that you can use to help you. The first thing is this particular equation is the only quadratic equation out of the entire 6 equations there. It's the only one that's going to have a parabola. So that's why I quickly identified this one. All right. You have 1, 2, 3 odd degree polynomials. 2, 3, and 6 have odd degrees. So that means the arms are going in different directions. 4 and 5 are your only even other than the quadratic. These are the only even. And the way you can quickly determine which of these two is either F or what? A. Is F or A. It has to be F or A because A and F are the only functions with the arms going in the same direction, and that's when you have an even degree. You just look at the coefficient, the leading coefficient. The leading coefficient for number 4 is positive 1. So that means the arms are going in both directions. And the leading coefficient for 5 is negative 1, which means the arms are both going down, which is A. So the other things you can determine from looking at these graphs, let's take a look. I just want to spend a little bit of time with number 2. Let's take a look at number 2. F of x equals 3x minus x cubed, and we've matched it with this particular graph. So let's take a look at that. So if I give you on a quiz, I'm just going to pick out here graph. Oops, I didn't mean to do that. Whoa, how'd that happen? Oh, all right. I didn't really want to do that, so let's take that out. So let's focus right here on graph C. this graph. And I'm just going to move this down the page. And then the equation that goes with it. So if we have this graph with the equation that goes with it, which was f of x equals, help me, it was 3x minus x cubed. Okay, so the first thing I would do with this is I would put it in descending order. That's what I tend to do with all of my functions, is I put it in descending order, which means your highest degree function first. Okay, and now you can look at your degree. Your degree is 3, which means you could have up to 2 relative max extrema, one in this case, which is a relative max, which is right here, it's your relative max, and the other one is a relative minimum. And what else did the rest of that phrase say was important? And it has at most, and there's different pieces of this, at most n real zeros. What does real zeros mean? What does that adjective mean when it says real zeros? Nope. Nope. I'm not asking where it is. I'm not asking where it is. What does real mean? Real zeros, that language real. Why didn't I just say at most n zeros? Why bother putting real in? All real numbers, right. Okay. That's right. So this is important because starting on Friday, we're going to be looking at complex imaginary numbers. So as far as real numbers go, this is the most number of real numbers you can have. So if we look at this function right here, it has degree 3. So it has at most 3 real, put the word number in after that if it helps you, real number zeros, which we know translates to as an image 3 x-intercepts. So that's the most number of x-intercepts. It can have 3. And if you look right here, there they are, 1, 2, 3. Those are your 3 zeros of your function, okay, or your 3, and that translates to 3 x-intercepts. But what that also translates to, those x values are the solutions to this equation. You take your function and you set f of x equal to 0. So you set your function equal to 0. And to find those 3 values, you solve this equation. So zeros, you don't write down, when I ask you for the zeros of a function, I hate taking off of this on quizzes and tests. When I ask you, I often will give you a little table like this. List your zeros and list the multiplicity of each zero. This is often what I will do. What you should be putting here is just the value of x that solves this equation. It's the solution set to this equation. It's the actual value of x that solves this equation. Now we could look at this graph. This definitely looks like 0 is one of the zeros. Anytime you see that, automatically that means that x or some power of x is a common factor to the polynomial. That's what that always tells you. When you see a 0 at the origin, then that means x or a power of x is a common factor to your polynomial equation. And if you look at this equation right here, you see x is common to each term. So that helps you with the first step of factoring this. You can pull out x as a common factor. In fact, I don't like having a -1 as my leading coefficient. So I'm pulling out -1x. So I'm going to pull out -1x, and I'm going to factor what's left. So what's left inside would be x squared. My signs are going to change, -3. Okay, so I have factored that as my first step. Now, depending on who you are, how you proceed from here will be different. There's a couple of different approaches, actually 3 you could take. No, you can't take x squared out because x squared is not common to both of these. So right now you can say, all right, I can see that one of my factors, I have to set both factors equal to 0 to solve this. So you say negative 1x equals 0, and you know that's going to happen when x is 0. So one of the zeros is x is 0. What are the other 2 zeros? The other 2 zeros are the solution to this quadratic equation. Now, how you solve this quadratic equation is totally up to you. You know 3 different methods. One is to use the quadratic formula. That's one method. The other method is to extract the roots. And when you extract roots, you often forget half of your answers. But if we were going to extract the roots, I would set x squared on one side and my constant on the other, and remember that it's plus or minus the square root of 3. So one of my roots is square root of 3, and the other one is the negative square root of 3. And then the other way to do this is to factor it. And anytime we have an x squared term and a constant, we know our factors look identical except for one's a positive and one's a negative. And the number that sits right here is the square root of whatever that number is. So there's your other way to do it. And again, your solution here is plus or minus square root of 3. So the zeros for this function are negative square root of 3, 0, and square root of 3. What I do not want to see under here is the factors like x plus square root of 3 or x minus square root of 3. I don't want to see the factors. I want the solutions to the equation. That's what the zeros of a function are. It's the values of x that make that equation equal to 0. Now, if you completely factor this, folks, if you completely factor this to get the multiplicities, if you have the graph, you can look at the graph. If you don't have the graph, then just look at the exponents on each factor. The exponent on each of these factors is 1. It's odd. So what does that tell you happens at each of these zeros? What does your graph do? It crosses your x-axis. So this has multiplicity 1, 1, 1. And when I graph at each of these zeros, I expect my function to cross the x-axis and change sign. That's what I expect. It's not going to turn around like if it were an even multiplicity. It's going to cross. And if you go back here and you look at this particular picture, here's negative square root of 3 comma 0. Here's 0, 0. So these are now the coordinates of the x-intercepts, square root of 3, 0. Notice your function at all 3 of those zeros crosses right through your x-axis and changes sign from positive to negative in this first case. You go from being above the x-axis to below, and at the 0 at the origin, you go from being negative before to the left of 0, and then you're positive to the right of 0, and then again at positive square root of 3, you change your sign from above the x-axis to below. That's the type of investigation you now should attempt to do when you go back and look at each of these equations. Okay, now some of these you can factor, some of them you can't, but if you notice here, the first thing you see when you look at number 3 is x is a common factor. So what point on your graph do you know is going to be a 0 or an x-intercept? The origin. Exactly right, Jasper. And when you pull an x out of here, you have a quadratic left. You have a quadratic left. So you can get the exact solutions. Like on here, we can't tell. It looks like it's close to -5, and it looks like it's close to 2. So you use the quadratic formula on that to get the exact value of your zeros. Okay. So that's the type of thing to prepare yourself for the next quiz and test you could do, is not only matching these equations, but asking yourself, how many zeros does it have? And what's the multiplicity of each zero? Now, sometimes I could just give you a graph and ask you that same question if they went through at exact points, what the multiplicity of each zero is. So that's the type of thing you should be heading towards with this activity. All right, so in order to prepare us for today's class, if you were to use a polynomial to model the population size of a growing city, over time, would you use a positive or a negative leading coefficient and why? So we're using some type of polynomial. We don't know what degree it is. It could be an odd degree or an even. And you are trying to look at its end behavior, because when you say over time, you're going out, letting time go on and on and on. Would you think a negative leading coefficient or a positive coefficient would make the most sense and why? Julia? Yeah. Right. Well, it would be. With a positive leading coefficient, whether it's an odd degree or an even, whether it's odd or even degree, you know your right arm is up in the air. It's rising. End behavior rises. So if the city is growing, it makes sense that over time, the population will be growing. If you have a negative leading coefficient, the population is going to be falling, and it will eventually be negative, which is meaningless. That's what we called model breakdown. All right, so let's take a look at this scatter plot right here. We don't have a context for it. We just have some data points. We have 0, 10, looks like 2, 7.5, 3, 3. Okay, we've just got these data points plotted. And I'm trying to determine some polynomial that I think would fit this the best. What degree polynomial would you choose to model this behavior? Which one? What degree? 4. If I hear a 4, do I hear anything different than a 4? Ken was thinking 3, so Mahendra says 4. Ken thinks 3. You go with 4. He changes his mind. Why 4? There's 3 turning points, right? And n minus 1 gives you 3, and that's the number of turning points. 4 minus 1 is 3, and that's the number of turning points. Because if you just try to sketch some type of model through this data set, it might look something like that. So you have 1, 2, 3 turning points. Okay. So that's the type of thing we're going to be doing throughout today's classes, is you're going to try to pick a model, a polynomial model. Now remember, you have linear models and quadratic models at your disposal, but now you would have a cubic. And if you look at your calculator, what Caitlin and I did this year is we're avoiding all of the steps for doing this on your calculator, because you spent more time when we did linear regression and quadratic just figuring out what buttons to push. But if you went in here and you went over to calculate the number of tests, notice you have a linear regression, which we've used, and that's of the form ax plus b, which is your slope and your intercept. Then we've done the quadratic regression. So if I had these data points right here, I would put those data points into my calculator, and then I would hit a cubic regression model to try to model those data points. And I would get a statistic called R squared that would tell me how good my model is. But we're cutting out that part of the class because that's more something that would be suitable to a full stat class. And we're giving you this information, but I just wanted you to see on your particular calculator where you could get these models. This stands for a quartic model, which is 4th degree. And then it goes into another linear regression. Notice that's the same as 4. It's just got the slope first. Because in algebra, we do it in this way, and in statistics, we always start with the y-intercept, but they're exactly the same thing. Then we get into exponential and logarithmic regression, which is the last week of class. So your only purpose today will be looking at the class activities, reading, and then answering the questions. We've done all of the graphing for you with GeoGebra. Please do me a favor, however, you notice there'll be some equations on your graph that doesn't say equals y. So when you go through your class activities, would you do that for me? So let's figure out this demo. So far, we've looked at linear and quadratic regression. So let's take a look now at data that is not necessarily straight. If you look at all of your different examples in the class activity, they're data that does not fall in a straight line. So we have other choices other than linear regression to model data. So let's take a look at this first one. This is the number of women in the full-time civilian labor workforce measured in millions of women. And this excludes women in the military and probably women in that are incarcerated. So this is the number of women in the full-time civilian labor force with children under the age of 6, and I've selected 5-year periods from 1975 to 2000. This was taken from the U.S. Bureau of Labor Statistics. So let's take a look at this. I used GeoGebra to create the scatter plot below. You see we have 1, 2, 3, 4, 5, 6 data points. This is the actual data, and these are the points that represent each of those data points. So then I asked GeoGebra to fit a linear model, a line of best fit, which is the red line, and this is the equation for that line. And then I asked it to fit a quadratic model through it. And as you can see, both models fit the data pretty well. The red line is very close to each of these data points. And actually, the parabola fits each of those data points a little bit better. Okay, so each model is going to give you a good estimate from 1975 to 2000, right? So from within the range of your data, 1975 to 2000, both models look pretty decent. Okay, so let's see how they may differ. So let's go out now. Oops, I guess that y equals got moved. Yeah, put that there. Let's take a look at each model and write the equation down and use it to make a prediction. So the equation for the regression line is y equals 0.2111x plus 3.9919. Why do you think I carried each of those values out to 4 decimal places? Why didn't I just call it like 0.2 and 4.0? Why didn't I estimate it, do you think? Why do you think I carried it out 4 places? So, and so the equation for our regression parabola is negative 0.0048x squared plus 3.3799x plus 2.8662. So they're given to you. You didn't have to put them in a calculator and get them yourself. So that saves you a lot of work. That's what I just went through with the calculator. Remember I just showed you? Yeah, by GeoGebra. Yeah. You could, but it would take you a very long time. There are equations to calculate these coefficients here. Yeah. Okay, but that was in the days before technology. The only other thing I want to remind you is that you should put a little hat on Y, that little caret. That's to remind you that the value of Y that comes out of this equation is always an estimate. It's based on a model. It's not the actual data. So that's what I would do to remind myself. So let's make a prediction. We want to make a prediction to see how many women would be in the labor force in 2011. Well, it would be a prediction on this based on this model because the model only goes to 2000, but it would actually be an estimate because we're in the year 2015, right? So 2016. So how would this model estimate the number of women in 2011? How would the linear model estimate that? What would we do to find that out? Would I put 11 into the equation? 41, right. How'd you get that, Spencer? Yeah, it's the years after 1970. That's what X is. So you always have to read how each variable is defined. So basically, you go, okay, I'm going to predict the number of women in the workforce using the linear model by putting 41 in for X. And then to use the parabolic model, I put in 41 for X there. And I get two different answers. So I'd like table 1 and table 2 to do this first one here and get the answer and confer with each other. And then the rest of you, tables 3 through 5 to get the answer for the parabolic model. Just confer with each other and see if you have exactly the same answer. Linear model, in fact, if we just took a vertical line and we took that line and we dropped it right down where 41 is, just to estimate it here, right? You can see that your linear model is definitely predicting a lot more millions of women than your quadratic model. So this is approximately going to be 41, 12 point, did you say 647? 647. And this point is going to be approximately 41, 10.373. Okay. So the question is, which of these models do you think may be more accurate? We notice that both models is very close to the actual data up to 2000. But now we're going out into the future. Remember, going beyond your data set, it's called extrapolation. We are extrapolating. And it's always dangerous territory when you get too far beyond your data set. Okay, so all I know is that I'm looking at the trend here. And the trend here looks like that the numbers of millions of women in the civilian labor force looks like it's starting to level out a little bit. So maybe this quadratic, the parabolic regression, might be the more accurate. But I really don't know what's going on socially, economically, and culturally. But if I was researching this, I might know. And maybe I would have a better idea because I live in the United States. But if this was another country, I would be really hesitant to pick one of these models to go beyond this data set. So you have to, there's a lot of concerns. And right now, I don't have what I think is the answer, the right answer. But I would pick one of these, and then I would give an explanation for why I would pick it. One explanation for picking the 10.373 is exactly what I said. The trend appears to be leveling out, so I would pick 10.373. I might say, well, after the year 2000, we had a change in presidents for 8 years, and the economy started to take a nosedive. We also went into war for Iraq, which meant more men were leaving the US and more women were going into the workforce. That's what happened, like with Rosie the Riveter in World War II. So I actually expect the number of women to increase, and I'm going to pick the linear model. So there are ways that you can explain right now either one of these models that might make sense. Okay? As a researcher, you're going to know your data very well. Whether you're in environmental science, you're in business, you're in management and marketing, you're looking at the stock market, whatever your interest is. If you're in a STEM field, you'll be looking at models all the time. Just a couple of weeks ago in the New York Times, there was a big article that said computer models for predicting how fast the ice shelves were melting in Antarctica was off, that they were melting much faster and being destroyed much quicker than any model previous to that. Every time you read about climate change and rising sea levels, this is all using very sophisticated mathematics and computers. So this is really relevant to your life. We have to look at it at a fairly simple level right now. And then depending on where you go in your career, you could get much more complicated than these models. But this is the type of thing you would do. All right, so if I were to use the leading coefficient test, because notice with my linear model, my slope is positive. So my right arm would be rising as I go out in time. But my parabolic model has negative leading coefficient, which means my right arm would be going down. My population, the number of women in my workforce would be decreasing and eventually be what, according to the model, the end behavior?
It's a number of women.
Yes. Yeah. Yeah. So what would be happening with this model, because the leading coefficient is negative over time? It would not only get to zero, what else would happen? It would go into negative right numbers of women, which we know has absolutely no meaning. And that's where this model would completely break down. So if we looked at the far right hand end of the model and we looked at the leading coefficients, I'm not sure if either one of these models would be accurate into the future. But if I had to pick one, I would probably pick the linear. If anything, I'd be overestimating, but I certainly wouldn't be saying that there were zero and negative women in the workforce. But right now, I wouldn't pick either one until I had more data. I wouldn't feel safe making any kind of prediction. Okay, so that's all you need. Read through this modeling process and how you select a model. The main idea for selecting a model is that if you have several different models that get very close to your data, you always want to pick the simplest equation possible to model the data. Okay, as your degree increases, your data tends to rise very quickly or fall very quickly. So in terms of end behavior, higher degree polynomials aren't always very suitable. So you have half an hour or 25 minutes left. You should be able to get through most of your class activities today. There are a wide variety of activities asking you different number of questions. So hopefully this will be fairly comprehensive. As usual, let me know if you need any help.